All right, so we're here doing malware analysis, and we'll start with, the point is you have a Windows machine, you have malware, you don't know what it is, and there's basic things you can do to learn about it. The simplest one, now we're going to use the fake malware samples. They're already in that machine if you downloaded the machine from me. If not, you can download them here, but you will have to turn off Windows Defender, because this is not real malware, but it does have the signatures to real malware. So if you have antivirus, it will freak out and tell you you're downloading 100 viruses. So you have to have whatever, that's why you have to have a special malware analysis machine, which not only is isolated from your other machines and doesn't have any private information on it, but also doesn't have any defenses. And therefore it's not safe to use for normal purposes. That's why you make a special VM for this purpose. So the first thing, of course, which we looked at earlier, is just upload the file to VirusTotal. You just upload any malware to VirusTotal, and that will just tell you if it's known to be a virus in any of the antivirus products. And then it will do some other tests. You can see what network connections it makes and such in the behavior tab, as we saw last time. And then we can do other things to learn what's here. So aside from VirusTotal, one good tool to use is PEView. So let me see, I want to open labo101.exe. Okay, so first, they're all pre-installed on this machine. PEView, this lets you see the structure of a Windows executable. And like I said, the main thing you're going to learn in this malware analysis is how Windows works, because you have to understand how Windows software works in order to understand how the bad guys are abusing it. And the malware samples are on the desktop in this folder, Practical Malware Analysis Labs, and in there's Chapter 1, and labo101.exe is the first sample. So this is the thing you get used to in malware analysis. This, the main lesson right here is what Windows executables look like. They always start with MZ, and then they have a legacy hub, a legacy stub from MS-DOS. This program cannot be run in DOS mode, and all this stuff is just boilerplate that's always the same. Then down here at 512 bytes in or so, you have the PE, that's the portable executable file header, and all modern Windows software is portable executable file format. So this is where the real action starts. And you can view it this way, just in a plain hex editor, and see the general structure of it. And you'll see some readable stuff. These are the sections. Portable executable files always have certain sections. The text section, one important rule about Windows is everything is named the opposite of what it is. So the text section contains machine code, which is unreadable. Any readable strings would be in like a data or an RData section, or resource section. And so these are the section headers with information about where the sections are, and then you have gaps, and then down here, this looks like the unreadable machine code, just random bytes. And then later on, here's Windows API calls. Now, if you're running Windows software, your software runs in userland, a limited privilege environment of the desktop and the command prompt. You don't have kernel privileges, which means you can't touch any hardware directly. Only the kernel can, and only Microsoft can touch the kernel, with a few exceptions. Our hardware drivers come from your hardware devices, and unfortunately antivirus products also mess in the kernel, although Microsoft has been trying to kick them out for 10 years. And anyway, but your userland program, like your browser and your word processor, cannot touch any of the hardware, can't even read the keyboard or the screen. All you can do is ask the Windows operating system to please do that for you. It's like you're an executive that can't get your hands dirty. You have to ask the mailroom to do the work. And so all your Windows program does is call Windows API functions. Open a window, read the keyboard, put something on the screen. That's all you're doing. So your program is doing, and the API calls all look like this. They have these several words capitalizing the start of each word, and you get used to the description of them. So these are create a file mapping, create a file. So some part of this program will create a file. These are the names of things it calls. These are the libraries it gets them from, these DILs. So you load the libraries, and the library has hundreds of functions, and you use some of those functions. So here in the header, it's defining what libraries it's going to use and what API calls. And then down here are the strings the developer typed into it. You can see things like this will destroy your machine. And you already can spot something right here. This is kern.e132.dil. Now that is supposed to look like kernel32.dil, which is a legitimate Windows file, and this is a very common malware trick. They make a program that looks like an innocent file, but it isn't. So right away, the reason you do malware analysis, I should say, is to find indicators of compromise typically. There are only a couple things you want when you analyze malware. One is, how do I detect if other machines are infected? So I want to find indicators of compromise, like a file or a network connection that it makes, or registry key. And the other thing is I want to know what damage it did and how to fix it. So you don't want to know everything about it, you just want to know those things. And right away, we can see some indicators of compromise here. It apparently creates this file. And in fact, I even know where it goes. See Windows System 32, apparently it's going to create that strange file in this directory. So that strongly suggests that's how I can detect it. Now, all right, and so that's the game here. So this is one way to analyze it, is just scroll through the raw hex file, but this program parses it into meaningful chunks for you to make it a little more reasonable. So here you've got the stub header that contains no useful information. Here's the NT headers, and here's the signature, which is just the NT, PE, to tell it's a pure. Here's the file header with things like a time date stamp when it was compiled, which is often used to guess what country it came from. And you've got information here about the size of the file. And then here and down here, you've got the export table and the import table, and those will list all the functions it uses in libraries. And if it's an executable, it will only have one export, only one way in. If it's a library, it will have many exports because it offers many functions. And so then here's the text section. It tells you how big it is. That's the header, which just tells you how big it is and where it is in memory. And the same thing for RData and data. And here's the actual contents of the text editor. And like I say, it just looks like random bytes because this is raw machine code. That's executable code. Here's the RData, and that has your import address table. And here it is, that list of all the function calls and libraries it uses. And it has to know that in order to load the program. Microsoft Windows uses dynamic library loading, so instead of including library functions in the executable, which would be static linking, it uses dynamic linking, so when you launch the program, it then separately tries to load the libraries. And the reason it does that is if you have a program that uses something like networking, and there's some other program running that also uses networking, when you launch the second one, it doesn't load a second copy of the library. It detects that the library is already in memory and connects to it. Now this makes programs launch faster and consume less memory, but it's dangerous and unsanitary, and this is the number one way you execute code on Windows machines, is by tricking it into loading a library file that's bogus. Since it's constantly connecting to other code outside the program, it's pretty easy to trick it into loading the wrong library. So, but it's done, that's how we're doing it. That's how Linux is doing it now too. And here's, so this program, one of the clues that it's malicious is it uses very few libraries. A normal Windows software would use 10 or 12 or more libraries. This has only 2 because this program doesn't do much at all. And as you can already see from the names of the libraries, you can guess it creates a file of some kind. It does some kind of hunting for a file and creating it. And down here, these are low-level functions like command lines. It's doing a string comparison and allocating some memory. So it's doing something like searching through a list of files and comparing it to a string to see if a file is there and then creating a file, which is also very common because one thing malware does is it tries not to infect the same machine twice. So it'll typically look to see if it's already infected, and only if it's not infected will it infect it. So these are the kind of functions you'll see. And here's the import directory showing the libraries it uses. Here's the name table with the name of each function like the last one, and just more information about it. And there's the data section, which in this case just has a few defined strings. So you can examine it this way, and you get a pretty good view of what's happening in the file. That's PE view, and there's a flag defined there. Another program that's useful is PEID. And I guess I'll use this, PEID. All right, what this program does is it just knows the file signatures of hundreds of possible file types. So if you feed it in any file, and I'm going to go to my malware sample, which is desktop, malware, binary, chapter 1, 1.exe, it guesses the structure of the file and gives you information the same way the other one is about the different sections. But the new thing is it guesses what language it's written in, recognizing it. So this is a Microsoft Visual C++ file, so it was probably created with Visual Studio. This turns out to be pretty handy. It can detect exotic file types like we're going to see in the next section. Anyway, that's one thing you can get from that program. By the way, you have a lot of tools that often overlap doing the same thing, and that's a good thing because the bad guys know the tools and they deliberately write malware that fools your tools. So if a tool gives you strange answers, you try another tool. And you just expect that. You're dealing with intelligent adversaries, and they do try to fool you. So bintext, I mentioned before, is probably your number one tool because it's so easy to use and so easy to understand. This is just a graphical version of the command line strings on Linux. Although it does look for both ASCII strings and Unicode strings. Microsoft uses a really old 16-bit Unicode and you have to look for those kind of strings. It just automatically does that. So if I browse and open that file here, malware analysis binary 1, this one, and then go, it shows me all the readable. Now all this does is search through the file byte by byte, and whenever it finds a series of printable characters that's 4 characters or longer, it prints them. So it doesn't know that these are strings, it doesn't know they're API calls, it doesn't interpret them at all. So you will get some random junk like this, that is just random characters that happen to be printable. But anything printable, you'll find it. So here's the thing you always find about DOS mode. Here's a name of a subsections text in our data. Here's some Windows API calls. Here's some more low-level Windows API calls. Here's those strings we saw before. This indicator of compromise, C Windows System 32, Kearney 132, and then down here is more API calls, and that's it. So it's a pretty simple program.
Is it
Yeah.
analyzing the executable or the library?
You can do either one. So treat them just the same. And by the way, libraries are also portable executable files. There's only one bit of difference. There's a bit in the header to say if it's a library or executable. Other than that, they're the same. And the other difference is, of course, libraries have many exports. There are many ways in. Executables only have one way in, only one export. It's a good question. Anyway, so that's I always use this first because it's so easy. The problem is they could encrypt the strings or something, and then you wouldn't see them here, and we'll see that. Anyway, that's another bit of static analysis, so-called. Static analysis, by the way, there's two kinds of malware analysis, static analysis and dynamic analysis. Static analysis is analyzing malware without running it. And there are two ways. One is the stuff we're doing here, a cursory examination where you feed it to a virus engine or look at the strings. The more advanced way, which is the only way I knew when I started, is to disassemble it in IDA Pro and read the assembly code. And that's why I thought malware analysis is heroic. That's a lot of work, very difficult. It turns out these modern tools mean you can get a lot done without doing that. That is your last resort. The most difficult thing to do is to read the assembly code and figure it out. You only do that when you have to, and only for small portions of it that are interesting. You use these other tools to try to learn what you need without putting that much work into it. And dynamic analysis is where you run the malware, deliberately infecting the machine. And that is easy and fun and very powerful. One of the most powerful techniques is you just run a bunch of monitoring tools on the operating system and then infect it. Now, when I first heard this, I rebelled. I said, wait a minute, the malware could be modifying the system. You're using the infected system to gather data. Isn't that sleazy? And they said, yeah, it is sleazy and inaccurate, but the fact is it usually works. And it is your fundamental philosophy, just like a cop. A cop trying to solve a crime doesn't find all possible evidence. You just find whatever's easy to find, and maybe that's enough. And you only dig deeper if you have to. So you try the simple technique and be aware that it's not perfect. Nothing is perfect. Most of the time, running your analysis tools on the infected machine is good enough. If it's not, then you try something else. And there's advanced dynamic analysis where you run the malware in a debugger so you can stop it and analyze it, function bit by bit. And we'll do all those things. So this is basic static analysis where you run simple tools to give you an easy look at what's in the file. All right. And then there's a tool called Dependency Walker. I don't think I'll demonstrate it because I find this to be pretty annoying for malware. The actual purpose of this file is to solve dependency problems in your Windows software. And so it opens it up and it shows you all the libraries and functions it uses and helps you find missing libraries. I find that these other tools are an easier way to see what function calls it's making. But anyway, this tool exists and some people like using it. All right, and so there's a few flags to find there. That's basic static analysis. And I'll stop this video and then I'll talk about basic dynamic analysis. Let me stop this one.